Good evening. This video is about the Buggy Lab that we are doing. It's actually called a constant velocity lab. We are going to be using these buggies as a way of kind of modeling what constant velocity looks like, but then also making and testing some predictions about when this buggy will either pass or collide with another buggy. A couple things to know. First off, you gotta make sure you give your buggy a good name. You can leave the names on there if you want to. We've got Snoop Dogg, and I can't see what the name is there. Shabla. The DeLorean for Back to the Future fans. Little Yachty, and Harold. So you come up with a name or sauce, or you could just stick with whatever one is on the side of there. That's totally fine. Obviously, be appropriate. But what we are going to do then is you are going to need to take some data down about each of these cars. That's why it's important that you keep the same car, is because you're going to be using the same car throughout the lab, and different cars might be going at different paces. And that's the first thing to point out about this lab, is that the red car versus the blue car. Red cars should go faster. You can see that the lights turn on and the little antenna is flashing. Compared to the blue car, it doesn't turn on if I set this up. Let's see if I can figure this out. Okay. So if I set them down, you'll notice that the red one goes considerably faster than the blue ones. We're going to grab them. First off, a little explanation about why that is happening. If you pop open one of these blue ones, you'll notice that I put a roughly battery-shaped piece of tinfoil in there, and then you can stick the other battery in there. And what that does, it's the tinfoil allows the electricity to still conduct through there. Notice I've got that. But since it's got half the voltage, it goes slower. It's not exactly half as fast. I'll let you kind of measure that and figure that out. But that's how these things are actually going slower. For some of you, it might be an army car that's your slow one. Or maybe, honestly, maybe even red car is your slow one. But you need to keep track of which one is your slow one, which one is your fast one. And then, as far as taking data, you're going to use some tape, meter stick, there's the meter side, and permanent marker. You are going to make some markings on the ground. Notice that right here, you've got 0 meters. You use your meter stick to measure out another 2 meters, and you are going to measure all the way to a total of 10 meters. So 0, 2, 4, 6, 8, 10 meters. And what you'll be doing is you're going to measure how long it takes your car to get to each one of those points. You can plot that. It's an XY coordinate plane. The X would be how much time it takes. The Y would be what distance it gets to. And we're going to draw a curve or draw a linear plot of that car's speed. Now, once we do that, you can use that plot to actually test some predictions about if we start the one car at 0 meters, another car at 2 meters, will they pass each other? And if so, where and when will they pass each other? I'm going to show you a little bit really quickly about how we do that on the board here. So, sorry to hope I'm not making anybody dizzy with all this moving around. So, I'm going to use pink as, let's say it's our red one. At time 0, they should always start at a position of 0, and then whatever, let's say at 2 meters, let's say it was 10 seconds, then you'd fill, it took them 10 seconds to get there, you'd put that there. And then at 4 meters, it took them 20 seconds, you'd put that plot there, and so on. And then it's a really good idea to use a ruler. Don't just freehand this like I'm doing. You can draw a line. Now what you're going to be able to do with that is, let's say I ask you to start that instead at 10 meters. I want to start that car at the 10 meter mark instead of at the 0 meter mark. Well, if you know the slope of this, the rise is 2. You can figure out how far and how long it takes that car to go. So this has a rise of 2 for a run of 10. I can erase that. Well, if it starts at 10 and I flip it the opposite direction, it should have a rise of -2 and a run of 10 still. So there's that point. 1, 2, and 10. And what you should see is a line that looks very similar to that first line we drew. What that means is after 2 seconds, after 10 seconds, that car would be at 8 meters. After 20 seconds, that car would be at 6 meters, and so on. And now where this can get fun for us is if you draw the line for, I'm just making this up, if you draw the line for your slower car, right there is the point where those cars would collide. You can make a prediction about what time that would be, and you can make a prediction about what distance those cars would collide at. So that's what we were going to be doing, is first off modeling the shape of those graphs. Hopefully you know after Match That Motion game today what a straight line means versus a curved line, what it means to be going up versus going down, what it means to be steep versus being shallow. Those are all things you should know before we start this lab. And then we're going to get into kind of the more the nitty-gritty with this lab. Other few things to think about are variables, control variables. One really big control variable is probably maybe the biggest one is how straight this is traveling. You might have noticed when I let both of these go, the blue one was going pretty straight, the red one is going off to the side. If you think about it, if you are stopping the time at 2 meters, but it actually is going diagonal, it's actually traveling further than 2 meters. So the time that you're recording is actually longer than what it should be. So you're not accurately measuring that car speed. So you always want to have it be going as straight as possible. Another thing you want to think about is, do you start the front of the wheels on the tape? Do you start in the middle or do you start at the back? It doesn't really matter as long as you are being very consistent. I like to think about the front as the reference point because it's going to make more sense when they collide. That the front of one car will collide with the front of another car, or when they pass each other, the front of one car would get passed by the front of another car. Other control variables, making sure that you've done good, accurate measurements with the tape, that it actually is at 0, 2, 4, 6, and 8. Making sure that you time it very accurately and record that. Making sure that you plot that accurately and draw your curve. Probably the other biggest control variable that unfortunately we can't control very well is the batteries inside of here. Now you are sharing this with other classes, so what that means is it might have a certain battery level for your class when you're in mesh 1, 2, 3, or 4 today, but then when you have that again tomorrow or Wednesday or Thursday or Friday, whatever day you're doing this on, it's going to actually be run down a bit, which might make that car go a little bit slower. So unfortunately, there's no good way to control for that unless we had separate cars for every single group throughout the whole grade, or if you popped out your batteries every time and saved those batteries. Neither one of those is very practical. So what we actually will have to do a little bit later in the lab is recalibrate, which means you'll have to kind of re-time your car to make sure it's still going the speed that you said it's going or that you think it is going. As far as I can think of, another big control variable, if you lose your car, if you accidentally forget which one you were using or somebody else steals your car, that could be problematic. Making sure you're doing it on the same surface. We're going to be doing this on carpet, but let's say that you do it inside the classroom one day and then you do it outside the classroom another day. That could be a pretty big control variable. Those are mostly it. Maybe if a fifth grader kicks it accidentally and you keep that trial. So you want to think about what those control variables are. You want to minimize them as much as possible so that your data is accurate, because your data will determine how good your predictions are. That's about it. Have a good night.